This video will cover Section 3.1, Part 1, Relations and Functions. Students will be able to represent relations, identify domain and range, and determine if a relation is a function. First, let's review a relation. A relation can be defined as either a set of inputs or outputs, or a set of ordered pairs. And we can represent a relation in three different ways. First, using a set of ordered pairs with the input comma the output, or x comma y. A mapping diagram where we draw arrows to show each input with each output. A table of values with the x as the input and the y as the output, or as a graph. Now let's practice representing relations in all three methods. So first, for a giraffe, this data set, it gives us information about a giraffe in the form of a table, where it says their age on the left and their height on the right. Now with a mapping diagram, what you're going to do is you're going to draw an arrow from each piece of information. So first I have 18 for the age, goes with the height of 4.25. So I would draw an arrow from my age of 18 to my height of 4.25, because we assume that the x goes in the left column, or the left oval, and the y goes in the right. Then I have an age of 20, goes with a height of 4.40. So I can draw an arrow from 20 to 4.40. Next I have my age of 21, goes with a height of 5.25. So I can draw an arrow from 21 to 5.25. Then I have an age of 14, goes with a height of 5.00. So I can draw an arrow from 14 to 5.00. And lastly, I have my age of 18, goes with the height of 4.85. So I can draw an arrow from 18 to 4.85. So this represents how each input, or x, relates to each output, or y. Next, for the ordered pairs, I'm going to write each of these ordered pairs in a set of parentheses using brackets around them. So I'd have my bracket to represent this is the full set. Then I'm going to use my first set of information. So the 18 and the 4.25 will be my first order pair. So I have 18, comma, 4.25. Then my next one, I'm going to graph the 20 with the, or plot the 20 with the 4.40. So I'll have 20, comma, 4.40. Then I will have the 21 with the 5.25. So I'll have 21, comma, 5.25. Then I have my 14 with the 5.0. So I'm going to have 14, comma, 5.00. And then lastly, I would have my 18 go with the 4.85. So I would have 18, comma, 4.85. And then I put my other bracket to show that this is the full set of ordered pairs. Lastly, I then am going to graph each of these points. So the first one, at 18, comma, 4.25, I'm going to estimate I have 18 is here on the x-axis, and 4.25 would be right here. So I can plot my point at 18, comma, 4.25. Then I have 20 with 4.0. So I can go over to 20 and estimate that 4.4 is going to be about here. So I can plot my point about here. Then I have the 21 goes with the 5.25. So I go over to 21 and up to 5.25, which is here, I can plot my point. Then I have the 14 with the 5. So I can find that point on my graph. So I would go to 14 and up to 5, which is right here. And lastly, I have 18 with 4.85. So I go over to 18 and up to approximately where 4.85 is going to be between the 4.75 and 5. And I can plot my point there as well. And we are going to leave these points as separate points on our graph for right now. Next, let's review the terminology domain and range. The domain is the set of all of the x coordinates in a relation. And the range is the set of all of the y coordinates. And to help you remember it, you can remember that domain always is first in the alphabet in comparison to range, and x is first in our ordered pairs. Now, to identify the domain and range, we know from the previous page that the domain is always the x's and the range is the y's. Now when I list these, you are going to use the curly brackets. So we're going to use these curly brackets, and we need to make sure that they're in increasing order. So smallest to biggest. Sometimes they'll already be arranged that way, and other times we're going to have to do that on our own. So if I look at the table example, again, we know that the domain is the x's. So if I want to list the domain, that means I'm considering each of these x values. So I'm going to identify that these are all my domain values. And if I want to write them out, we're going to say, okay, the domain, I'm going to use my curly bracket, and we're going to identify the smallest number and check to see if there's any repeating numbers. Now, all of them are individuals, so we don't have to double check. And now I'm just going to list them in order from smallest to biggest. So the smallest number is 1, then the next smallest is 2, the next one is 3, 4, and 5. So in this case, they were in order, but that won't always happen for us. Next, I need to identify the range. And the range, we know, is always related with the y values. So if I want to list the range, and we identify that all of these y values are my range, I'm going to see first, are there any repeated values? And if I look, I have the value of 13 listed 3 times. So I only need to consider it once. So if I look here, I'm going to include the first 13, and the second ones I'm already going to ignore. Now if I'm listing these in order, the smallest number is 11, the next smallest is 12, and then the next smallest or the biggest of all of them is 13, and I would close my bracket. Now for ordered pairs, we're still going to use the idea that the domain is the x's and the range is the y's. And when we know when we have an ordered pair, the domain or the x's are always the first number and the range or the y's are the second. So if I want to identify my domain, I'm first going to identify all the x coordinates. So I have 4, 2, -3, and 2. Now if I check to see if I have any repeating numbers, the number 2 is listed twice, so I'm going to ignore the second 2. And now I'm going to list these in order. So I'm going to put my curly bracket. The smallest of the 4, 2, and -3 is -3. The next smallest is 2. And then the only remaining x coordinate is 4. Now for the range, I need to identify all of the y coordinates. So my y coordinates are 3, -1, -3, and 4. None of these numbers repeat, so I'm going to have to include all of them. Now if I'm listing them in order, the smallest of this negative 1, this 3, negative 1, negative 3, and 4 is negative 3. So I can write a negative 3. Then my next smallest would be negative 1. Then next I would have a 3. And lastly, I would have the number 4. For the next example, for the mapping diagram, we again know that our domain is always the x's. So the first oval represents our x's, which is domain, and the second one represents our y values, which is the range. So if I'm going to list the domain here, the domain is all of my x values. Now, the nice thing about a mapping diagram is, for the most part, you shouldn't ever have numbers listed twice because then we would just have 2 arrows. The other thing is they usually are written in order. So if I'm going to list them, the smallest of the x values is negative 6. Then the next smallest is 1. Then I have a 2. And then my last number is 3. For the range, I'm going to identify the y values, which are negative 8, negative 5, and 7. And I'm going to list them in order again. So I'll have my range of, if my smallest number is negative 8, negative 5, and 7. For my last example, for the graph, we're still going to go through and list our domain and range, but we're almost going to just take it from the ordered pairs. So it's easiest in a lot of ways if I rewrite each of these as an x comma y. So my ordered pair for this point would be at negative 5 comma 3. This point would be at negative 2 comma 2. This ordered pair would be at 3 comma 2. And my last ordered pair would be at 5, negative 1. Now, if I want to identify my domain and range, I'm going to do the same process like we did with the ordered pairs. So the domain is, again, the x values. So if I'm going to identify my x values are negative 5, negative 2, 3, and 5. And we can see we don't have any repeating ones, so I could just go ahead and list all of them separately. So I put my bracket. The smallest of my domain is negative 5, so I can cancel that out. Then I have my next smallest is negative 2. The next smallest number is 3. And the last one will be 5. Then for my range, the range is the y values. So if I highlight my y coordinates and then check to see if I have any repeating values, there's 2 y coordinates with a value of 2, so I'm going to get rid of one of them. And now I'm just going to list them in order. So the smallest y coordinate is negative 1. The next smallest y coordinate is 2. And my biggest y coordinate, or the last one, is 3. And this provides you with examples of finding the domain and range from both a table, ordered pairs, a mapping diagram, and a graph. So all of our ways of representing relations. The next concept we'll talk about is a function. A function is a relation in which each member of the domain is paired with exactly one member of the range, where each input has one output. So all the x values in a relation must be different in order for the relation to be a function. Functions also must pass the vertical line test. What the vertical line tells us is that it will pass through a function only once, no matter where it is positioned. So for example, this first graph is a function because it only ever crosses it once. Versus the next example, This vertical line crosses this graph twice, so it's not a function. And the third example, in this place, crosses this graph twice, also making it not a function. So in order to determine whether a relation is a function, when you're given a set of ordered pairs, you're basically asking yourself, are all the x values different? So if I look, my x values here are 1, 3, 4, and 4. And what we should notice is that this value of 4 is repeated. So your answer would be not a function. The x value 4 repeats. The next one says we have -2, 0, -1, 0, 0, 2, 1, 3, and 2, 4. So my x values are -2, -1, 0, 1, and 2. Now all of these x values are different, so your answer is that it's a function because all the x values are different. In this example, we have to determine whether each table depicts a function. So essentially, we're still asking ourselves the same question, is are all the x values different? So for the first one, the x values are the column because it's a vertical table. So I have -2, -1, 0, 1, and 2. And these x values are all different. There's no repeats. So you could say it's a function, and your reason would be all the x values are different. For the second example, we are again asked to determine if it's a function. So if I look at the x values, I have 3, 4, 5, 4, and 10. However, we should identify that this value of 4 is repeated. So it would be not a function. And your reason would be that the x value of 4 repeats. The tables at the bottom are examples of horizontal tables, but the process is still the exact same. So if I identify my x values, I have 2, 2, 4, and 6. However, we should notice that this value of 2 is repeated. So this would be not a function, with your reason being the x value of 2 repeats. And in our last example, we now have to consider that we're given another horizontal table with the x values of 1, 2, 3, and 4. So in this case, all the x values are different, so it would be a function because all x values are different. And in this case, it doesn't matter that the y's repeat, all we're looking at are the x's. Now in the next example, we have to determine whether each mapping diagram results in a function by seeing how the x values go with the y values. In order for it to be a function, we're basically asking ourselves, does each x give only one y? So if I'm looking at the diagram, for the first one I have, this is an x, and this is the y's, and if we look, the value of 1 pairs with both s and w, and this is not a function because 1, or the input 1, results in s and w. If I look at my second example, I have these are the x's and these are the y's, and we can see that each x goes to only one y. So because each of these x's only matches with one of them, your answer is yes, each input has one output. For the next example, we are also checking to see does each x go with one y. If I look, the first circle is the x's, the second one is the y's, and we can see that each of these x values only results in one possible y value. Even though it's repeating a lot of these y values, all that matters is each x has one y that it goes with. So your answer would be yes, it's a function because each input has one output. And for our last example, if I look at these are the x's and this is the y's, I'm comparing how these x's match. Now what we should notice is this value of 6 goes to both s and t. So the value of 6 has two potential outputs. So this means that it's not a function because the input 6 results in s and t.
In the next example, it says to use the vertical line test to determine whether each graph represents a function. As I pass my vertical line through this example, I could say that it first crosses twice right here. So since it is crossing the vertical line twice, it is not a function. In our next example, as I move my vertical line through, at each point it's only crossing this line once. Since it only crosses once, I could say that yes, it is a function. For the last example, if I were to move my vertical line through, when I hit this first spot, I have that I'm passing through it twice. Since it's passing and touching the vertical line twice, no, it is not a function. In these next examples, we're going to do the same thing. So for my first one, if I move my vertical line through, it only touches once at each point. So this would be, yes, it is a function. In this next example, if I were to move my vertical line to this point, it is crossing it twice. So this would be, no, it is not a function. For the next example, if I move my vertical line, it crosses at each point only once. So I could say that, yes, this is a function. For the next example in the bottom left, as I move my vertical line, it only crosses it once. So I could say that, yes, it is a function. For the one in the bottom in the middle, as I move my vertical line, once I hit this point, it is crossing it more than once. At this point, it's actually crossing it 3 times. So it'll be the answer that no, it is not a function. Finally, for our last example, if I were to move my vertical line across, it only passes it once at each point. So I could say that, yes, it is a function.
Before we get into word problems, let's review the different types of numbers we have potentially for classifying our domain. Whole numbers are the natural counting numbers and zero. So they would be any number starting at zero and whole numbers getting bigger than that. So you have 0, 1, 2, 3, etc., and continue forever and ever. Integers are the natural counting numbers, their opposites, and zero. So for example, if we start with 0, we could have 0, then you could have 1, and -1, 2, and -2, 3, and -3, and this would continue forever and ever. But you'll notice that these have to be whole numbers, either positive or negative. And real numbers are the set of basically all the numbers we ever deal with. So this is any number, positive or negative, including fractions. So you could have a whole number, or you could have something like 2/3, -3.2, anything along those lines where we start dealing with our fractions. In this example, we have to analyze word problems for reasonable domains and ranges. So it says a function can model each situation. What is the reasonable domain and range for each function? Now it says a hose fills a 10,000-gallon swimming pool at a rate of 10 gallons per minute. Now if we identify our variables, x is going to be the number of minutes, and y is going to equal the number of gallons in the pool. Now, if we want to identify a reasonable domain, we'll remember that the domain is the x value. Now, if we think about the number of minutes we could possibly have, the smallest possible number of minutes is we could have 0, I could have 1 minute, you could have been doing it for 3.5 minutes, I could have been doing it for 10 minutes, etc. And there's no limit on how long this could go for. So this means that our reasonable domain would be any value greater than 0. And because of the fact that we could have a decimal, it's going to be any real number greater than or equal to 0. Now for the range, we're talking about the number of gallons in the pool. What we should notice is that the number of gallons in the pool is that we're filling a 10,000-gallon swimming tank. So we know that for our range, which is our y values, we're talking about numbers between 0 and 10,000. Now these could be anything. It could be a whole number. So for example, I could have 100 gallons. I could have a decimal. I could have 502.5 gallons. Okay, but it's some number between those two. So because of that, this would be any real number between 0 and 10,000. Because rather than just being any number greater, we have to limit it to it can't be greater than 10,000, because as soon as it became greater than 10,000, it would overflow the pool. In the next example, it says a restaurant needs to order chairs for its tables. One table can accommodate 4 chairs. So if we're determining what this is, the x is going to equal the number of tables, and y is going to equal the number of chairs. Now, if I want to identify my domain, which is my x values, I could start at 0, and then it could be any whole number after that. I could have 2 tables, I could have 5, I could have 10, but what I can't have is I can't have 1.5. So because of this, because of the fact that it's any number that's 0 or greater, this means that our domain is any whole number greater than 0. Because it has to be bigger than 0 and it can't be a decimal, making it a whole number. Now for the range, or the y values, we have to have 4 chairs at every table. So for example, I could have 0 chairs, I could have 4 chairs, I could have 8 chairs, 12 chairs, etc. But you'll notice that these are always multiples of 4. However, there isn't an upper limit of this. So this means that my range is any whole multiple of 4 greater than 0. Because I can't have a negative number of chairs. However, since I have at least 4 at every table, it's going to be some sort of multiple of 4.